This is the second video in our Random Forest series. In this lesson, we'll build a random forest classifier from scratch. In the previous video, we covered the basic ideas behind random forest and introduced bagging-based ensemble learning. We also discussed sampling techniques. Specifically, we looked at both row sampling and column sampling. In this lecture, building on those concepts, we'll implement a random forest model in 3 different ways. First, we'll build a random forest using scikit-learn's DecisionTreeClassifier. We'll use DecisionTreeClassifier to create the individual decision trees and then add row and column sampling to construct the random forest. Second, we'll use scikit-learn's random forest classifier. Since random forest is already implemented in this library, we can build the model much more easily. Third, we'll implement a random forest completely from scratch without relying on scikit-learn. Although this implementation is a bit more challenging to follow, it will help you gain a deeper understanding of how random forests work internally. Now let's get started. We'll begin by implementing a random forest using scikit-learn's DecisionTreeClassifier. Although DecisionTreeClassifier is normally used to build a decision tree classifier, here we'll use it to create the individual trees inside the random forest. We'll then add sampling functionality and a mechanism for aggregating predictions from multiple trees to complete the random forest implementation. We'll use the pre-processed Titanic dataset. Let's load the dataset. Here's what the dataset looks like. Next, we'll separate the features and the target variable. The survived column is the target variable, and all remaining columns are input features. We'll then split the data into training and test sets. We'll use 100 trees, and each tree will have a maximum depth of 3. Here, n denotes the number of training samples. Now we'll iterate 100 times, creating and training a decision tree in each iteration. The first step is row-wise subsampling. From the n training samples, we randomly select n samples with replacement. The sampled data, x sample and y sample, form the Bootstrap sample or sub-data set shown in this figure. Next, we create a tree using DecisionTreeClassifier. This corresponds to the individual tree shown in this figure. For column sampling, we set max features to the square root of the total number of features. As a result, whenever a node is split, DecisionTreeClassifier considers only a randomly selected set of features, just as we discussed in the previous video. We then train the model to the Bootstrap sample and store the trained tree in the model's list. Next comes the prediction phase. We pass the test data through every trained tree and collect their predictions. We then perform majority voting to obtain the final predictions and evaluate the accuracy. This corresponds to the final stage shown in this figure. Next, let's use scikit-learn's random forest classifier. With this implementation, building a random forest becomes much simpler. We'll set the Bootstrap sample size equal to the size of the training dataset and set the number of features considered during feature sampling to the square root of p. Here, P represents the total number of features. We then fit the model to the training data. Next, we use the model to predict the target class of the test samples. Finally, we evaluate the classification accuracy. After running the code, we get the following accuracy scores from the two models. The results are not exactly identical because each model is built using different Bootstrap samples and randomly selected feature subsets. Let's inspect the individual trees created by RandomForestClassifier. We can see that they are all DecisionTreeClassifier models. In other words, RandomForestClassifier builds an ensemble by combining many DecisionTreeClassifier trees, which is essentially the same idea as our first implementation. Now let's run the code. The results are as follows. Next, we'll implement a random forest completely from scratch. This implementation may look a bit more complex because it recursively builds binary trees, but it provides valuable insight into how the random forest algorithm works internally. Let's start by implementing the class that creates the base classifier used in the random forest. This code is based on the DecisionTreeClassifier class that we developed in Part 7 of the Decision Tree series. We've extended it by adding feature sampling at each split. If you're not familiar with that implementation, I recommend watching that video first. To fit more code on the screen, I've omitted most of the comments here. However, the source code provided with this video contains detailed comments throughout. For now, we'll focus only on the parts that were added to support random forests. A new parameter called maxFeatures has been added to the DecisionTreeClassifier class. This parameter specifies how many features will be selected during feature sampling. Feature sampling has also been added to the node splitting function. If maxFeatures is not specified, the algorithm behaves as before and uses all available features. If maxFeatures is provided, a subset of features is randomly selected without replacement. Feature sampling is performed every time a node is split. The selected features are stored in flist. Among those sampled features, we search for the best feature and the best split point. The rest of this code is identical to the previous implementation. Likewise, all of the code shown on this slide remains unchanged. Next, we'll implement the RandomForestClassifier class. This class uses the DecisionTreeClassifier we just discussed as its base learner and builds a random forest using an ensemble approach. The constructor takes three key hyperparameters that control the overall structure of the random forest. The first is n estimators, which specifies the number of decision trees in the ensemble. The second is max depth, which limits the maximum depth of each individual tree. As we discussed in the previous video, according to Leo Breiman's original random forest formulation, individual trees are typically grown to their maximum depth. However, in this implementation, we impose a depth limit and set the default value to 5 so that the resulting tree structures are easier to visualize later. The third parameter, maxFeatures, specifies how many features are randomly selected each time a node is split. Finally, we use the estimators list to store all of the trained base trees. Next, let's define the fit function, which trains the random forest using the given training data. The input X contains the feature values and Y contains the target labels. If max features is set to SQRT, we use the square root of the total number of features. Otherwise, we use the value provided by the user. Now we can begin creating and training the individual trees. We first generate a Bootstrap sample by randomly selecting n samples observations with replacement from the training data. In bagging-based ensembles, the Bootstrap sample size is typically chosen to be the same as the size of the original training set. This Bootstrap sample, or sub-dataset, will be used to train an individual tree. Next, we create a tree using the DecisionTreeClassifier class that we implemented earlier. This corresponds to the individual decision tree shown on the right side of the figure. We pass the max depth and max features values to this class. Row sampling has already been performed above, while feature sampling will be carried out inside each individual tree according to the value of max features. We then fit the model to the Bootstrap sample and store the trained tree in the estimators list. Next, let's define the predict function. We pass the input samples X through all trained trees and collect their predictions. A majority vote is then performed across all predicted classes, and the most frequently selected class becomes the final prediction. This corresponds to the final stage shown in the diagram. Next, let's import the RandomForestClassifier class and use it to build a random forest model for the Titanic dataset. We'll begin by loading the preprocessed Titanic dataset. Then we'll create the training and test sets. Next, we instantiate the random forest model. We'll use 100 decision trees in the ensemble. The maximum depth of each tree is set to 3. Normally, decision trees are grown much deeper, but we've kept them shallow here to make their structures easier to visualize. For feature sampling, we'll use SQRT, which is the standard default setting for random forest classifiers. We then fit the model to the training data. Next, we predict the class labels of the test samples and evaluate the model's accuracy. At this point, our random forest classifier for the Titanic dataset is complete. The test accuracy obtained in this example is 0.8161. As an additional step, we define a function that visualizes an individual trained tree. Starting from the root node, this function traverses the entire tree and prints its structure as text. I'll skip the detailed explanation of this code. Let's take a look at the first trained decision tree and examine its structure. The resulting tree structure is shown below. Here's the same tree shown as a tree diagram. As you can see, a cart-based decision tree with a maximum depth of 3 has been generated. Now let's run the code. The results are as follows. In this video, we implemented a random forest classifier in 3 different ways. In the next video, we'll explore the out-of-bag or OOB score.